You've probably seen the headline by now. Somewhere between a YouTube thumbnail and a Facebook post, someone told you that Google's quantum AI intercepted a signal from outside our galaxy. Maybe it was wrapped in dramatic music. Maybe it had a shaky voice narrating over stock footage of stars. Maybe it promised you the truth they don't want you to know. Here's the problem. It never happened. There is no signal. There is no interception. There is no message from beyond the Milky Way sitting in a server room in California. What there is, instead, is something almost as strange and completely real. A machine that may be borrowing computing power from universes we cannot see. A calculation finished in 5 minutes that would take a classical supercomputer longer than the universe has existed. A chip named after a tree that might be the first real step toward a computer that thinks in ways human brains were never built to understand. Forget the fake headline. Stay for the real one, because it is stranger than fiction, and every part of it is true. To understand why this story became so easy to twist into a fake one, you have to understand what Google's quantum AI team actually built, and why the people who built it started talking like science fiction writers instead of engineers. This is the story of Willow, Google's most advanced quantum chip, and the questions it forced some of the smartest physicists on Earth to start asking out loud, on the record, in front of cameras. For decades, quantum computing lived in a strange limbo. It was theoretically incredible and practically useless. Physicists knew that if you could harness the bizarre rules of quantum mechanics, the way particles can exist in multiple states at once, the way they can be entangled across distance, the way probability itself behaves differently at the smallest scales, you could build a computer that doesn't just calculate faster than anything before it. You could build a computer that calculates differently. Not a faster horse, a different kind of animal entirely. But there was always a catch, and the catch had a name. Errors. Quantum bits, or qubits, are notoriously fragile. Unlike the simple ones and zeros inside your laptop, qubits exist in delicate superpositions, and the moment they interact with heat, vibration, electromagnetic noise, or basically anything in the outside world, they lose their quantum properties. This is called decoherence, and for years it was the wall that quantum computing kept slamming into. You could build bigger and bigger quantum processors, but the bigger they got, the more errors piled up, and the more errors piled up, the less useful the whole system became. It was like trying to build a taller and taller tower out of sand. Every extra brick just made the collapse more likely. Go back far enough, and you'll find that the dream of a quantum computer wasn't born in a Silicon Valley lab at all. It was born in the early 1980s in the mind of physicist Richard Feynman, who stood in front of an audience and made a simple but radical observation. He said that if you want to simulate nature, truly simulate it, down to its smallest and strangest behaviors, you're going to need a computer that follows the same rules nature follows. And nature, at its most fundamental level, isn't binary. It doesn't deal in clean ones and zeros. It deals in probabilities, superpositions, and entanglement, concepts so counterintuitive that even the physicists who discovered them spent decades arguing about what they actually meant. Feynman's idea sat mostly as a theoretical curiosity for years, discussed in physics departments and academic papers, because building an actual machine based on these principles seemed, for a long time, almost impossibly difficult. The obstacles were not small. Every qubit, the basic unit of quantum information, has to be kept in an extraordinarily delicate state. Unlike a classical bit, which is simply on or off, a qubit can exist in a superposition of both states simultaneously, and it can become entangled with other qubits in ways that allow for a kind of parallel processing that classical machines cannot replicate. But that same delicacy is a curse. The instant a qubit interacts with stray heat, a stray vibration, or a stray electromagnetic field, its quantum properties collapse, a process called decoherence, and whatever information it was holding is lost or corrupted. Early quantum computers built in the 1990s and 2000s could hold a handful of qubits stable for fractions of a second, just long enough to prove the underlying physics worked, but nowhere near long enough to do anything useful. For a long stretch of quantum computing's history, skeptics reasonably wondered whether the entire field was destined to remain a beautiful theory that could never survive contact with the messy, real world. Companies like IBM, and later Google, poured enormous resources into chasing this problem down, building superconducting qubits cooled to temperatures colder than outer space, temperatures where atoms barely vibrate at all, in an attempt to buy a little more stability, a little more time before decoherence set in. Progress came in increments, more qubits, slightly longer coherence times, incremental improvements in error rates. It was slow, grinding, unglamorous work, the kind that rarely makes headlines because the milestones are measured in fractions of a percent rather than dramatic leaps. And yet, this grinding work is exactly what set the stage for Willow. Every earlier chip, every earlier failure, every earlier incremental gain in coherence time was a brick in the foundation that eventually let Google's team achieve something the field had been chasing since Feynman first raised the idea: a quantum system, where adding more qubits made things more stable instead of less. This is where Willow changes the conversation. In December of 2024, Google's quantum AI team announced a chip that didn't just add more qubits. It solved, for the first time in a real physical device, the problem that had haunted quantum computing since its inception. As they scaled up the number of qubits, the error rate went down instead of up, exponentially. This is called being below threshold, and it is the single most important milestone in making quantum computers actually useful instead of theoretically interesting. Sundar Pichai, Google's CEO, called Willow an important step in the journey to build a useful quantum computer, and for once, the corporate language was actually underselling what had happened. Here's what makes this so significant. Every previous attempt at quantum error correction had a frustrating property. You'd link qubits together into what's called a logical qubit, hoping that by combining several fragile physical qubits, you could create one more stable logical one. But historically, adding more physical qubits to the mix just introduced more chances for something to go wrong. Willow flipped that equation. Google's team tested error correction across different sizes of qubit grids, going from a 3x3 grid up to 5x5, up to 7x7. Each time they made the grid larger, the errors dropped by roughly half. That's not a linear improvement, that's an exponential one. And exponential improvements are exactly the kind of thing that turns a laboratory curiosity into a technology that changes the world. But the number that actually broke the internet, the number that turned scientists into storytellers, was about time. Google gave Willow a specific benchmark test, something called random circuit sampling. Think of it like this. Imagine a machine designed to produce an extremely specific, extremely complex pattern of random-looking numbers, one that is fantastically difficult to reproduce unless you actually run the exact quantum process that created it. It's not a useful calculation in the sense of solving climate change or curing disease. It's a stress test, a way of proving that a quantum processor is doing something a classical computer fundamentally cannot do, or at least cannot do efficiently. Willow completed this benchmark in under 5 minutes. To put that in perspective, Google stated that one of today's fastest classical supercomputers would need 10 septillion years to complete the same task. 10 septillion. That's a 1 followed by 25 zeros. If you tried to write out that number in seconds, you'd run out of universe first. The age of everything, from the Big Bang until this exact moment, is roughly 14 billion years. 10 septillion years doesn't just dwarf that number. It makes 14 billion years look like the blink of an eye by comparison. Willow did, in 5 minutes, what would take the best classical machine on Earth, a span of time so long that the concept of years almost stops meaning anything. Now, it's worth being honest about what this benchmark actually represents, because part of why the story spiraled into misinformation is that people skipped this part. The random circuit sampling task has no direct practical application. It doesn't cure a disease, it doesn't design a new material, it doesn't decode a message from space. Its entire purpose is to be something that's fantastically hard for a classical computer to fake, so that when a quantum computer does it fast, you have proof that quantum speedup is real and not just theoretical. Physicist Sabine Hossenfelder, reacting publicly to the announcement, pointed out exactly this. The specific problem is chosen because it has been mathematically shown to be difficult for classical machines, not because the answer itself is useful. That's an important, honest caveat, and it's also exactly the kind of nuance that gets deleted the moment a story goes viral. But here's where things take a genuinely fascinating turn, and where science starts to sound like something out of a late-night philosophy conversation. Hartmut Nevin, the founder and lead of Google Quantum AI, made a comment about Willow's results that, once you actually sit with it, is one of the wildest things a serious scientist working for a major tech company has said in public in years. He suggested that the fact Willow could complete this benchmark so astronomically fast lends credence to the idea that quantum computation might be happening across parallel universes. He described it in terms connected to the many worlds interpretation of quantum mechanics, an idea first proposed by physicist David Deutsch back in the 1980s, which suggests that every quantum event causes reality to branch into multiple coexisting versions of itself. In this view, when Willow performs a calculation, it isn't just crunching numbers in isolation inside a refrigerated chip in a lab. It might be tapping into computations happening in adjacent branches of reality, borrowing processing power, in a sense, from other versions of the universe running in parallel to our own. Let that sit for a second, because this isn't a fringe blogger's fantasy. This is the actual head of Google's quantum computing division connecting a real, measured, benchmarked result to one of the most mind-bending interpretations in all of theoretical physics. He wasn't claiming certainty. He was pointing out that this result is consistent with, and arguably supportive of, a picture of reality where the universe we experience is only one thread in an unimaginably vast tapestry of coexisting possibilities. It's easy to see how a claim like that, even stated carefully and with appropriate scientific hedging, becomes fuel for exaggeration once it leaves the mouth of an actual physicist and enters the churn of online content. Quantum computer taps into parallel universes becomes, a few reposts later, quantum computer receives messages from other dimensions, which becomes, a few more reposts later, quantum AI intercepts signal from outside the galaxy. Each step feels like a small exaggeration, but stack enough small exaggerations together and you end up with a headline that has nothing to do with the original science at all. So let's ground ourselves back in what's real, because the real story doesn't need embellishment to be extraordinary. Beyond Willow's headline-grabbing benchmark, Google's quantum processors have been doing something arguably even more important for the future of science: actual physics simulation. In research published in the journal Nature, a team that included scientists from Google Quantum AI, Princeton, and the Technical University of Munich used a quantum processor to simulate a category of physics called gauge theory. Gauge theories are the mathematical backbone of the standard model of particle physics, describing how fundamental forces and particles interact. In this study, researchers used the quantum chip to observe how particles and the invisible connective threads between them, sometimes described as strings, evolve over time. They could tune the properties of these strings, watching them fluctuate, stretch tightly, or even break apart, all inside the quantum processor. Pedram Raushan, one of the co-authors from Google Quantum AI, described it directly. By harnessing the quantum processor, the team studied the dynamics of a specific gauge theory and observed how particles and the invisible strings connecting them evolve over time. Tyler Cochran, a graduate student at Princeton and the paper's first author, explained that by adjusting the model's effective parameters, they could tune the properties of these strings, watching them fluctuate strongly, become tightly confined, or break entirely. This isn't science fiction. It's a real peer-reviewed demonstration that quantum computers can simulate the fundamental rules governing matter and energy with a level of direct physical insight that classical computers struggle to match. Why does this matter so much? Because classical computers, no matter how powerful, hit a wall when trying to simulate quantum systems. This is actually one of the founding insights behind quantum computing itself. Physicist Richard Feynman pointed out decades ago that if you want to truly simulate nature, and nature is fundamentally quantum mechanical, you need a computer that is also fundamentally quantum mechanical. A classical machine trying to simulate a quantum system has to approximate, simplify, and cut corners because the computational resources required to track every possible quantum state grow exponentially with the size of the system. A quantum computer, in theory, doesn't have to approximate at all. It can behave like the very physics it's trying to model because it's built from the same quantum rules. This is the real frontier, and it's a far more interesting frontier than any fake alien signal. If quantum processors can reliably simulate gauge theories, the mathematical language of forces like electromagnetism and the strong nuclear force, then scientists gain a tool to explore questions that have been stuck on chalkboards for generations. Questions about quark confinement, about the exotic states of matter inside neutron stars, about phase transitions in the earliest moments after the Big Bang. None of this requires intercepting anything from outer space. It requires building better tools to model the universe we're already inside of, using the same quantum weirdness that governs subatomic particles to power the very machine doing the modeling. There's also a wider ripple effect worth understanding, because Willow and its successors aren't just about esoteric physics simulations. Quantum computing, once it becomes reliably error-corrected and scalable, opens doors across an enormous range of fields. In medicine, quantum simulations could model molecular interactions with a level of precision that helps researchers design new drugs and understand protein folding in ways that are currently computationally out of reach. In materials science, researchers could simulate new superconductors or battery chemistries atom by atom, discovering materials that would take years, or might never be found, through classical trial and error. In cryptography, the flip side of quantum power is quantum risk, since sufficiently advanced quantum computers could theoretically break many of the encryption systems the modern internet relies on, which is why entire fields of research into post-quantum cryptography have sprung up in recent years to prepare for that eventuality. In climate modeling, quantum systems could eventually help simulate atmospheric and oceanic systems with a granularity that today's supercomputers cannot achieve. None of these applications are science fiction anymore. They're the reason governments and companies around the world are pouring billions of dollars into the quantum computing race, not because it makes for a viral headline, but because whoever solves the reliability problem first gains an enormous scientific and economic advantage. And that reliability problem is exactly what Willow was built to attack. It's worth walking through in a bit more detail why the exponential error reduction is such a big deal, because this is genuinely the heart of the story, more than any speculative multiverse commentary. Quantum error correction works by encoding one stable, reliable logical qubit using many physical qubits working together, using redundancy to detect and correct errors without actually measuring, and therefore destroying the fragile quantum state itself. For years, the theoretical promise of this approach ran into a brutal practical wall. As engineers added more physical qubits to improve error correction, the additional hardware introduced more opportunities for noise, more chances for something to go wrong, and the system's overall error rate often got worse instead of better. It was a bit like trying to fix a leaky boat by drilling more holes to bail water out faster. Willow demonstrated, across multiple qubit grid sizes, that this trend could finally be reversed. As the grid size increased from 3 by 3 to 5 by 5 to 7 by 7, the logical error rate was cut roughly in half each time. That is the exponential suppression of errors that Google's team had been chasing since the field's earliest days, and it is the single result that transforms quantum computing from an interesting laboratory experiment into a credible path toward a genuinely useful machine. There's a reason this milestone excited serious scientists far more than any fictional alien signal ever could. A signal from outside the galaxy, if it were real, would be a discovery about what else exists out there. Below threshold quantum error correction is a discovery about what we can build here on Earth with our own hands, using the strange rules that govern reality at its smallest scale. It's a tool, not a message. But tools, historically, have changed the world far more reliably than any single discovery of a message ever could. It's also worth pausing on why stories like the fake alien signal claims spread as easily as they do, because understanding that helps you spot the next one before you fall for it. Real quantum computing news is genuinely mind-bending on its own. The idea that a chip might be borrowing computational power from parallel universes doesn't need embellishment. It's already almost too strange to believe. That's exactly the soil that misinformation grows in. When the true story already sounds like science fiction, it becomes incredibly easy to nudge it just a little further into outright fabrication. And most people won't notice the seam where fact ends and fantasy begins. A benchmark computation involving random number distributions becomes, with a little creative rewriting, a mysterious calculation from beyond our world. A physicist's careful, hedged comment about the many worlds interpretation becomes a definitive claim that machines are communicating with alternate realities. And eventually, with enough retellings, a quantum chip running an error correction test becomes, somehow, a device capable of intercepting a signal from a galaxy millions of light years away, despite having absolutely no connection to radio astronomy, telescopes, or signal detection of any kind. None of Google's quantum AI hardware is designed to receive anything from space. That's not a criticism. It's simply not what the technology does. Detecting signals from beyond our galaxy is the job of radio telescopes, arrays like the ones used by projects such as the Search for Extraterrestrial Intelligence, instruments built specifically to capture and analyze electromagnetic radiation across the cosmos. Quantum. Processors like Willow live in dilution refrigerators, cooled to temperatures colder than deep space itself, isolated as much as possible from any external electromagnetic interference, precisely because their entire function depends on being shielded from outside signals, not receiving them. A quantum chip picking up a message from another galaxy would be, quite literally, the opposite of what these machines are engineered to do. They are built to be exquisitely sensitive to internal quantum states, while being aggressively insulated from the outside universe. It would almost be poetic if it weren't so thoroughly untrue. So where does that leave us? Now that the fake headline has been cleared away and the real one is standing in its place, it leaves us with a genuinely thrilling moment in the history of computation. A chip that solved, in a real physical device, the exponential error suppression problem that had stumped the field for decades. A benchmark result so fast that it forced one of the most respected names in quantum computing to publicly entertain the idea that reality itself might be far stranger and far more layered than everyday experience suggests. A separate but equally real body of research demonstrating that quantum processors can simulate the fundamental forces of nature with a fidelity that classical machines simply cannot match. And an entire horizon of future applications, from medicine to materials, science to cosmology, all resting on the same foundational breakthrough that Willow represents. None of this requires an alien signal to be extraordinary. If anything, dressing it up as one cheapens what actually happened. The real story isn't about receiving a message from somewhere else. It's about humanity building a new kind of thinking machine, one that operates on the same strange rules that govern electrons and photons and the fabric of space-time itself, and using it to peer more clearly into the universe we already live in. Willow isn't a receiver. It's closer to a new kind of eye, one built not out of glass and mirrors like the great telescopes that came before it, but out of qubits, superconducting circuits, and temperatures colder than the space between stars. The next time you see a headline claiming Google's quantum AI intercepted a signal from beyond our galaxy, you'll know exactly where that claim came from. Not from a discovery, not from an intercepted transmission, but from a chain of small exaggerations, stretched across blog posts and video scripts, each one nudging a real and remarkable achievement a little further from the truth, until what's left barely resembles the science that inspired it in the first place. The truth, as it usually does, turns out to be more interesting than the myth. Google didn't hear from another galaxy. It built a machine that might, in some strange and still not fully understood way, be borrowing help from universes running parallel to our own, just to finish a calculation in 5 minutes that would otherwise take longer than the age of everything that has ever existed. That's not science fiction. That's Tuesday at Google Quantum AI, and it's only the beginning of what these machines are going to help us understand about the universe we're actually living in. There's a broader lesson buried in this story too, one that goes beyond quantum chips and error correction rates. We live in an era where genuinely extraordinary science is happening constantly, quietly, in labs most people will never visit, published in journals most people will never read. And because that real science often sounds so strange on its own, it has become almost effortless for it to be repackaged, exaggerated, and sold back to us as something even stranger, something that didn't actually happen. The antidote isn't cynicism, and it isn't dismissing every wild-sounding headline out of hand, because sometimes the wild-sounding headline turns out to be true, or at least defensible, the way Nevin's multiverse comments were. The antidote is curiosity paired with verification. It's asking where a claim actually came from, tracing it back past the reposts and the rewritten scripts, all the way to the original source, the actual paper, the actual press release, the actual scientist's actual words. Almost every time you'll find that the truth was interesting enough on its own. It didn't need the embellishment. It just needed someone willing to slow down and tell it properly. Consider for a moment what Google's quantum roadmap actually looks like from here, because Willow was never meant to be a finish line. It was a proof of concept, a demonstration that the fundamental engineering obstacle standing between quantum computing and quantum usefulness could be overcome. The next stages involves scaling up further, building processors with more logical qubits, pushing toward what researchers call fault-tolerant quantum computing, a state where the system can run long, complex calculations with confidence that errors are being caught and corrected fast enough that they never accumulate into a wrong answer. Google has talked publicly about a multi-year roadmap toward this kind of large-scale, fault-tolerant machine, one capable of tackling problems in chemistry, material science, and optimization that remain completely out of reach for classical supercomputers, no matter how large those classical machines get. This is the quiet, unglamorous, genuinely historic work happening in the background while the internet argues about fictional alien transmissions. It's also worth remembering that real efforts to detect signals from beyond our solar system do exist, and they deserve attention in their own right, without needing to be falsely attached to quantum computing headlines. Radio telescopes around the world, as part of long-running projects searching for extraterrestrial intelligence, continuously scan the sky for unusual patterns in radio waves, patterns that might indicate an artificial origin rather than a natural astrophysical process. These efforts have been running for decades, using instruments purpose-built for exactly this kind of detection, instruments that look nothing like a quantum processor and operate on entirely different principles. If humanity ever does detect a genuine signal from another galaxy, it won't come from a chip cooled in a dilution refrigerator running an error correction benchmark. It will come from an array of radio dishes, pointed at the sky, built specifically for that singular purpose, staffed by astronomers who have spent their careers preparing for a moment that, as of today, still hasn't arrived. Conflating that entirely separate field with Google's quantum hardware isn't just inaccurate, it does a disservice to both fields, blurring the very real, patient, decades-long work of radio astronomy with a fabricated narrative that has nothing to do with it. So here's where this leaves us, standing at the end of the fake headline and the beginning of the real one. Google's quantum AI team didn't intercept anything from outside our galaxy. What they did was arguably more remarkable, in the way that real breakthroughs often are. Quiet at first, easy to miss if you're only skimming headlines, but genuinely transformative once you understand what actually happened. They built a chip that solved a problem the entire field had wrestled with for decades. They watched that chip complete a calculation so fast that the numbers involved stop feeling like numbers and start feeling like abstractions, 10 septillion years compressed into 5 minutes. They listened as their own lead scientist suggested, carefully and with appropriate hedging, that the result might be evidence for one of the most profound and unsettling ideas in modern physics, that reality itself might not be a single thread, but an uncountable tapestry of parallel branches. And separately, using the same underlying quantum hardware, they helped demonstrate that these machines can simulate the fundamental forces governing matter itself, opening a door toward a future where our deepest questions about the universe might be answered not by looking outward through a telescope, but by looking inward into the strange, elegant, still not fully understood mathematics of the quantum world. No signal arrived, no message was decoded, nothing came from beyond the Milky Way. What arrived instead was proof that human beings can build machines that operate on the same rules that govern reality's smallest and strangest behaviors, and that when we do, even the people who built them start asking questions that sound less like engineering and more like philosophy. That's the real story. It didn't need an alien signal to be extraordinary. It already was.